All right, so like I said in the last video, in chapter 1, we worked with linear functions that have a constant rate of change. And in this chapter, we're going to look at functions that have a constant relative rate of change. And they turn out to be exponential functions. Now, that relative rate of change is over a fixed interval, right? So if you looked at the relative rate of change from 2 to 4 over, t equals 2 to t equals 4, that should be the same as the relative rate of change from like 6 to 8, right? So you have an interval of 2. That's the interval width is 2. But it would not be the same if you tried to compare the relative rate of change from 2 to 4 to the relative rate of change from, say, 6 to 10, because that interval width is different. Okay, so there has to be a fixed interval width when you have the the relative rate of change has to be is constant over a fixed interval width. All right, so let's look at this next problem. In this next example, we have tribbles that have invaded the grain storage compartment of Starship Enterprise. And tribbles are known to reproduce at an alarming rate. Their population grows by 20% every hour. So if the initial population is 10 tribbles, what is the population after 1 hour? All right, so let's call our function p. And so we're going to look at p at 1. We know that p of 0, right? P at 0 is equal to 10, right? That's what we're told here, that initially we have 10 tribbles, so we want to know, okay, what is the population when after 1 hour? So our time unit is in hours. So the population grows by 20% every hour. So essentially we're going to have the 10 tribbles that we started out with plus 20%, 0.20 of that population, right? Now I can write this as 10. I can factor out, see, I have a constant, I could just calculate it as it is, but I want to point out that you could factor out this 10 and you would have 10 plus 1.02. So the quick way to add, whoops, not 02, that was the last example, 20, all right, 1.2, or you could just write it 1.2 if I wanted to. All right, so the quick way to add 20% to a function is just to multiply it by 1 plus the percent increase, okay? Because you're taking 100% of it and then adding 20% more. So either way, you're going to get 12 tribbles after the first hour. All right, so let's look at the population at 2, right? Now, we're going to have 12, and then we're going to add 20% of 12, right? Because we're told that the population grows by 20% every hour. Now, that is 12 times 1.2, right? And that is 10 times 1.2, right? Because 12, right? That's coming from here, this 12. That is 10 times 1.2, and then we're taking it times 1.2 again, okay? So I'm just pointing out, you could calculate it from this first expression, but I'm just pointing out where the exponential is coming in. So with either of these, any of these calculations, you'll get 14.4. Now, I don't know if that, a 0.4 of a triple is possible, but I'll just go ahead and write it out. So we have 14 triples and another one on the way. All right, at 2 hours. So now let's look at 3. Hour 3, basically we have, we're starting out at 14.4 and we're adding 20% of 14.4. And we can do a similar thing. That ends up being, that's the same thing as 10 times 1.2 times 1.2 times 1.2. So it's 1.2 cubed. And you can verify this for yourself, but essentially I can just take this expression for 14.4, right? This is 14.4, and replace it. Replace 14.4 with that 10 times 1.2 squared. All right. So we have 17.28. 17.28 triples. Okay, so 17 triples and 1 on the way. All right. So we want to write an expression now for the population of triples after t hours. All right. So you can see after 1 hour we have 10 times 1.2 to the first power. At 2 hours we have 10 times this is 10 times 1.2 squared, and then we have 10 times 1.2 cubed. So at an arbitrary time t, we're just going to have the initial population times 1.2 to the t power. Right? So we get an exponential functions. All right, I'll see you for the next video.